Okay, let's move on to chapter 3, which is pressure and fluid statics. So, don't try this. Just don't try this. So this is flying a cluster of 72 helium-filled balloons over California in April of 2003. The helium balloons displaced approximately 230 meters cubed of air, providing the necessary buoyancy force. Again, don't try this at home. But look how awesome that is. And look, he even had, I see one is popped. That's amazing. I guess he has a backpack on. Still, that's going to be a no for me. Here's our objectives. Not going to go through all of them because we are doing them. So pressure, what is pressure? It's a normal force exerted by a fluid per unit area. Okay, so 1 Pascal equals 1 Newton over meters squared. Okay, and then they have 1 bar, 1 atmosphere, 1 kilogram force over centimeters squared. You've got a bunch of them. Okay, and then here, this is just saying, again with the schematic, this is just saying that there are different pressures, right? So if you have someone who is 150 pounds versus someone who is 300 pounds, those pressures are going to be proportionally different. You have the same area of the feet, which is 50 inches squared. And you see that that pressure, that PSI is double because the weight is doubled. So the normal stress or pressure on the feet of a larger person is much greater than the feet of a slim person. And then here's some pressure gauges. Absolute pressure is the actual pressure at a given position. It is measured relative to the absolute vacuum or absolute zero pressure. So here, let me get my pen. Here, if you have just your atmosphere pressure, right here, just your regular atmosphere pressure here, and you have absolute pressure here, then the remaining of that is going to be your vacuum pressure. What is vacuum pressure? It's the pressures below the atmospheric pressure. Okay, so it's just what's left. And again, these three have relationships, right? So you can see that gauge pressure. So you have absolute pressure here, and then you have atmosphere pressure. And what is gauge pressure here? Gauge pressure is the difference between the absolute pressure and the local atmospheric pressure. Okay, and so most pressure measuring devices are calibrated to read zero at atmospheric pressure so that they indicate gauge pressure, right? So most of what we have, most of these pressure measuring devices are going to start here and are going to give you a 0, right? And so what they're wanting to measure here is a gauge pressure. And then the really fancy ones will then also measure this vacuum as well. Okay? So pressure at a point. Pressure is the comprehensive force per unit area, but is not a vector. Okay? Pressure at any point in a fluid is the same in all directions. Pressure has magnitude, but does not have a specific direction, and thus is a scalar quantity. So what this is saying it's the same, right? The pressure here is same to the pressure here, is same to the pressure here, same to the pressure here, same to the pressure here. There's a bunch of formulas. What this is doing is it's summing up these forces here. And the forces acting on a wedge-shaped fluid element in equilibrium. And so this is an XZ axis with changes in Y here. And so you have the change in X and the change in Z and the change in Y. And so you have just different pressures acting on each, and it gives you the formulas that go with that. So pressure 1 is the change in Y times the change in Z, which is here. And then the easiest one here, which is the change in x, is the change in x times the change in y. And then here you have the change in y L. Okay? And remember, we're looking at normal too. Remember? So we do have variation of pressure with depth. We have a free body diagram here of a rectangular fluid element in equilibrium. And again, here we have pressure coming in on each side, P1 over P2, looking normal too. And you have different changes that vary with the depth. You can see these changes. Okay? And over here, the pressure of a fluid at rest increases with depth as a result of added weight. Okay? And so you see here, we're starting up here. We don't have a lot of pressure up here. It's just atmospheric pressure. But as we're getting lower, well, we've got this much water pressure coming up. And now we have this much, and now we have this much water on top of us. It's just like diving, where you have to depressurize because you're coming up, or you can't go to the bottom of the ocean because there's too much pressure. There's just too much water on top of you. So here in a room filled with gas, the variation of pressure with height is negligible. That's because we really have to do things like go to the bottom, of the ocean really far down, or we have to go to very, very tall mountains to really see those. But when we're talking about just filled with rooms, we're not going to take a measurement, not in this class anyway. We're not going to take a measurement here and a measurement here because the difference here is just going to be negligible and it's not really going to matter for us. Okay, and so here is a pressure in a liquid at rest increases linearly with distance from the free surface. So it's just saying that right here, height is very impactful. And it's more impactful when you're talking about examining the height or depth within a liquid versus the height or depth in air. Here, the pressure is the same at all points of a horizontal plane in a given fluid, regardless of geometry, provided that the points are interconnected by the same fluid. So what this is saying is it's saying because this is straight, right? So this surface tension right here, this surface area, is much straighter than my pen drawing. And you see that this force is becoming greater as we're going down in depth, right? And so when we get all the way to here, as long as all of this is connected, which it is, it's all connected by the same fluid, this is different, right? Because that's mercury, we're not counting that. But the same pressure here is here, is here, is here, is here, is here, is here. So what that means, it means you can dive here and experience the same pressure. You can dive here and experience the same pressure. You can dive here and experience the same pressure. But the points here and here, H and I, those are not going to be the same. You cannot dive to the point in H, which is in mercury, and experience the same pressure as I. It's going to be a different pressure because you're in a different liquid with a different density. So with that, we have Pascal's law. It's the pressure applied to a confined fluid increases the pressure throughout by the same amount. So P1 equals P2. And that's evident here in a jack. So if the pressure applied to a confined fluid, and so you have the fluid inside of the hydraulic lift or the hydraulic mechanism, the fluid increases the pressure throughout by the exact same amount. So it's a 1-to-1 ratio here. And it's because of the displacement in area, and additionally because the liquids are essentially incompressible, right? The area A2 over A1 is called the ideal mechanical advantage of the hydraulic lift. And so that shows, you see A1 and P1. And so if you apply a force here, it's going to displace, if it goes down to here, it's going to displace this amount of liquid, and it's going to go over here, and it's going to lift it up by a proportional area of the displacement of the liquid in state 1. A barometer. Atmospheric pressure is measured by a device called a barometer. The atmospheric pressure is often referred to as a barometric pressure. A frequently used pressure unit is the standard atmosphere, and that's ATM, which is defined as the pressure produced by a column of mercury, which is 760 millimeters in a height at 0 degrees Celsius under standard gravitational acceleration. And remember, this right here is a constant that we use because we're on Earth. And this is just showing you the basic barometer. And so P atmosphere equals rho GH, and this G is that gravitational constant, 9.807 meters per second squared. The length of the cross-sectional area of a tube has no effect on the height of the fluid of the column of the barometer, provided that the tube diameter is large enough to avoid surface tension, capillary effects. So remember, if you have a really skinny barometer, you may have a severe capillary effect, right? But as long as you get to a cross-sectional area like this where you're not experiencing that, anything above it will be fine. It will not have an effect. So at high altitudes, a car engine generates less power and a person gets less oxygen because of the lower density of air. So remember, we talked about that when you're looking at the difference in the floor to the ceiling, right, in density, it's going to be negligible, and we don't compute that. But when you're talking about extremely high altitudes, you can't experience that. A manometer is a commonly used device to measure small or moderate pressure differences. A manometer contains one or more fluids, such as mercury, water, alcohol, or oil. And so you see here, you have one working fluid in orange, and then you have a second working fluid, which is a gas, in the purple. And so you see you have the start and then state 2, and then you have a height that you can actually measure the difference. So P2 is equal to P atmospheric plus rho GH, and then H will come from this height displacement because you are starting here. We always have a starting point, and then you are calculating it at a state 2. Okay? And remember, this G is a constant, and this rho, which is density, right, you would just get from your fluid. Some manometers use a slanted or inclined tube in order to increase the resolution or precision when reading the fluid height. Such devices are called inclined manometers. This is a similar phenomena to if you were in high school in a chemistry class and they said, hey, read your beaker at eye level so that you can get an accurate reading. This is the same thing, slanted or inclined, things like that, so that you can increase the resolution or the precision when reading the fluid height, because that's incredibly important. In stacked up fluid layers, the pressure change across a fluid layer density, rho, and height is rho GH, right? So this rho GH is the pressure change, okay? So you have rho, which is the density, right? So we have here, density, gravitation, 9.807. And then the height is, I'll just say given, even though it's not really. So you have the pressure at the atmosphere, right? So this is our point one. This is what we're looking at. We are calculating for this. Okay, so we're calculating for this point. And so we need to know everything above this, right? We need to know everything above this. And so you can do a bottom-up approach. You can start at 3 and 2 and then 1 and then atmosphere. But most people start a top-down, right? So you have the atmospheric pressure, you're going to have that. And then you need to add in all of the items for fluid 1, which is its density, a gravitational constant, and then the height of that, right? So the height here. And then you're going to need to add that. So it's just the sum of all of these. And so you're going to need the same thing for fluid 2, the density of that fluid, because it's a different density, right? The same gravitational constant, and then that's height that's given. And then the same thing for fluid 3, the density for that fluid, the gravitational constant, the height for this one, and that's going to equal the pressure at 1, right? Pressure at state 1. So here, measuring the pressure drop across a flow section or a flow device by a differential manometer, and so it takes a difference here. And so the flow section or flow device, and you see it's a single inlet and a single outlet with a return here. And so you have you have 1 here and then 2 here. And so what you end up with is you get 1 minus 2. So the difference here is equal to rho of the 2 states at GH, because this right here is excluded for P2. So what you're doing is you're calculating everything in here, and then and then the reduction of it is what you are able to get. This will make more sense that one will make more sense when we work it. The Borden tube consists of a hollow metal tube bent like a hook, whose end is closed and connected to a dial indicator needle. And then we have, and these are various types used to measure pressure. So, pressure transducers use various techniques to convert the pressure effect to an electrical effect. So this is taking the pressure technique or the pressure effect and then kind of like changing the language or giving you a different output in an electrical form. So voltage, resistance, capacitance, things like that. Pressure transducers are smaller and faster, and they can be more sensitive, reliable, and precise than other mechanical counterparts. Exactly, because we just talked about, let's see where this one is that we just talked about. This manometer where we have inclined versions, right? Or a slanted tube so that we can increase visually reading it. Well, if we can get a pressure transducer that can just spit out a answer, it's going to be much more precise and much more sensitive and therefore much more precise, right? Strain gauge pressure transducers work by having a diaphragm deflect between 2 chambers open to the pressure inputs. And so this measures the strain on the material and is able to map it. The piezoelectric transducers, also called solid state pressure transducers, work on the principle that an electric potential is generated in a crystalline substance when it is subject to mechanical pressure. So these are pressure gauges that you are able to embed in a material and then do a compression test on, and it will measure it from the inside. Those are piezoelectric transducers. Deadweight tester is another type of mechanical pressure gauge. It is used primarily for calibration and can measure extremely high pressures. So that way you're able to calculate some other types of pressure gauges. A deadweight tester measures pressure directly through application of a weight that provides a force per unit area. It is constructed with an internal chamber filled with a fluid. It's usually oil. And this is for other reasons, to decrease in friction, it helps with the parts being lubricated and letting those last as long as they can, along with a tight-fitting piston, cylinder, and plunger. Weights are applied to the top right up here. Right up here. Weights are applied to the top of the piston, which exerts a force on the oil in the chamber. The total force, F, acting on the oil at the piston oil interface is the sum of the weight of the piston plus the applied weights. So you're adding not just all of this, but also the weights, right? This is the introduction into fluid statics. Remember, we've been working primarily in dynamics, and that's the bulk of it. That's also what this class is, fluid dynamics. And remember, fluid mechanics is split into two portions, dynamics, and then with a very, very small part of statics. And while we won't go into too much detail, it is important for you to just know from a theoretical aspect what it means, so that if anything else, when you are in your career and you come across something like this, you will understand and know at least the difference, right? So fluid statics deals with problems associated with fluid at rest. Remember, dynamics is changing. It's a fluid in motion, right? And so this is at rest. It can either be gas or liquid. Hydrostatics is a fluid that is a liquid. Aerostatics is a fluid that is a gas. That's the same. Okay? And so in fluid statics, unlike dynamics, there's no relative motion between adjacent fluid layers, and thus there's no shear or tangential stresses in the fluid trying to deform it. The only stress that you do deal with in fluid statics is normal stress, which is the pressure. And the variation of pressure is due to only the weight of the fluid. And you do have that, right? So if you're diving down in an ocean, if you're not dealing with anything, if somehow you're able to have a completely still, non-deforming ocean, or if you're diving into a tank, right, a tank of water, and we're negating the energy transfer that your body is actually creating in the water, with the water, then you would still have pressure and stress on you as you dive down from the weight of the fluid. The topic of fluid statics has significance only in gravitational fields. Otherwise, everything would just float around. It wouldn't matter. The design of many engineering systems, such as water dams, liquid storage tanks, require the determination of forces acting on the surfaces using fluid statics. That's because it's stationary, right? The water is going to be stationary. So here's hydrostatic forces on a submerged plane forces. So I'm not going to go into too much, but we will define what a plane is. On a plane surface, the hydrostatic forces form a system of parallel forces, and we often need to determine the magnitude of the force and its point of application, which is called the center of pressure. And that's Hoover Dam. It's amazing. Here it looks a lot like the same. When analyzing hydrostatic forces on a submerged surface, the atmospheric pressure can be subtracted for simplicity when it acts on both sides of the structure. And also when you go deeper and deeper and deeper into the working fluid, the pressure is going to increase. Here's another one. It's talking about the center of pressure, right? Defining the center of pressure here. And then we have pressure distribution, pressure prism, pressure surface plane, things like that. Plane surface, sorry. So hydrostatic force on an inclined plane surface completely submerged in a liquid, it's just showing you where they are. We're not going to go into this because this is the dynamics course. But hydrostatic forces on a submerged plane surfaces, the pressure at the centroid of a surface is equivalent to the average pressure on the surface. So this centroid right here is the average. Remember, because the average may not always be the center. And this is the free surface, the top of the water. The resulting force acting on a plane surface is equal to the product of the pressure at the centroid of the surface. And the surface area and its line of action passing through. So this is just giving you that formula. It's explaining what it is. This is showing you the centroid and centroidal moments of inertia for some common geometries because it's heavily geometric dependent. And so you can see these centroid and centroidal moments. And this is pressure acts normal to the surface, right? So we have, this is a surface and it's normal to, if that was a straight line. And the hydrostatic forces acting on a flat plate of any shape form a volumes whose base is the plate area and whose length is linearly varying pressure. This virtual pressure prism has an interesting physical interpretation. Its volume is equal to the magnitude of the resultant hydrostatic force acting on the plate. So this is just saying that the volume is equal to the magnitude of the hydrostatic force acting upon. The projection of the centroid on the plate is called the pressure center. And therefore, with the concept of the pressure prism, the problem of describing the resultant hydrostatic force on a plane reduces to finding the volume. So it's just saying that we need the volume. There is also a special case, as there always is. It's the submerged rectangular plate. And we have these formulas here. Hydrostatic force acting on the top of a surface of a submerged vertical rectangular plate. Here's more. And hydrostatic force acting on the top of a submerged horizontal rectangular plate. And again, more. Very simple, pretty simple equations here. Hydrostatic forces on a submerged curved surfaces, again, just letting you see where the geometry is in the curved surface. Okay, in many structures of practical application, the submerged surfaces are not flat but curved, as seen here in the Glen Canyon Dam in Utah and Arizona. Oops. And here it is. It's another curve. So it's showing this dam that we just looked at. And those pressure points. In a multi-layered fluid, of different densities can be determined by considering different parts of the surfaces in different fluids. So what this is saying, and it's pretty applicable, is that if you have one item submerged in two different mixtures or two different working fluids, you will need to analyze them separately and then combine them, see the sum. You'll need to combine what you are able to find. Buoyancy force. The upward force a fluid exerts on a body immersed in it. The buoyancy force is caused by the increase of pressure with depth in a fluid. So here is a flat plate of uniform thickness H submerged in a liquid parallel to the free surface. And so you see here that you have not only a pressure down, but a pressure all up as well. And then this denotes our atmospheric pressure. And then we have a height of the plate and then a submergent depth. The buoyant force acting on a plate is equal to the weight of the liquid displaced by the plate. For a fluid with constant density, the buoyant force is independent of the distance of the body from the free surface. It is also independent of the density of the solid body. So this is just giving you relationships and then non-relationships. So here's a fluid, again, with the buoyancy forces. and this is Archimedes' principle, the buoyant force acting on a body immersed in a fluid is equal to the weight of the fluid that is displaced. Okay? So the force acting on the body is equal to the weight that was displaced by the body being submerged. And it acts upward through the centroid of the displaced volume. For floating bodies, the weight of the entire body must be equal to the buoyant force, right? So what is displaced is the upward force, so the weight of the body must be equal to this force for it to float, which is the weight of the fluid whose volume is equal to the volume of the submerged portion of the floating body. So this is when they're equal. And then this portion, just this. But when the whole thing is just kind of floating and it's filled, then you have neutrally buoyant. It's not floating and it's not sinking. And then here the density is greater than the density of the fluid. And so then you have a sinking, right? So when the density is equal to the density of the fluid, because remember, density is an independent property. Doesn't matter. It's not going to change. So when the density of this body is equal to the density of the fluid, it's going to just be suspended, middle. When the density of the ball or the floating body is less than the density of the fluid, then it's going to rise and bobble, probably. And when the density of the ball is greater than the density of the fluid, then it's going to sink. For a body floating on the surface of a liquid, the total weight of the body must be less than that of the liquid it displaces, right? Because you need to have less density than the water or the fluid. A portion of the body volume is submerged while the remaining portion is positioned above the surface of the liquid. Since the system is stationary, the two vertical forces W and FB must still be in balance. And so that's just showing this formula. And then here, this is for the Dead Sea. So the density in the water in the Dead Sea is about 24% higher than that of pure water. Therefore, people float much more easily with more of their body above the water in the Dead Sea than in the fresh water and normal seawater. So it's just because of the higher density. The altitude of a hot air balloon is controlled by the temperature difference between the air on the inside and the outside of the balloon. Since warm air is less dense than cold air, when the balloon is neither rising nor falling, the upward buoyant forces exactly balance the downward weight. And then it just kind of bobbles there. Stability of immersed and floating bodies. So you see you have A, which is stable, you have B, which is neutrally stable, and then you have C, which is very unstable. The stability is easily understood by analyzing a ball on the floor, right? So it's going to take actual momentum to get up either side. It wants to stay here. And here, it's going to stay here as long as nothing happens. And here, it is not going to stay here. Okay, and so here we have just the stability. So we have a floating body possesses vertical stability, while an immersed, neutrally buoyant body is neutrally stable, since it does not return to its original position after disturbance. And then here, this is showing unstable. Okay, and so this is restoring momentum when the center of gravity G of an immersed neutrally buoyant body is not vertically aligned with the center of the buoyancy. It is not in an equilibrium state and would rotate to its stable state even without any disturbance, because everything is trying to reach that equilibrium state. That's going to be an underlying theme in this course as well, and in anything that's a natural law. And so here you see stable, And this is stable, but it's trying to get back. It's trying to get back to that, trying to get back to here, really. And then this is unstable, and it's overturning. So it's just got too much. And you can see from where G, the gravity, is below the centroid or on the other side. So you see that the M is below the G here. So you see M is below, and that's unstable. And this metacenter here is above. And so that is stable, just in a correcting, in a restoring moment, or a correcting pattern. Fluids in a rigid body motion. Pressure at a given point has the same magnitude in all directions. We talked about that. It doesn't matter. It's going to be, here's this point. It's going to be going everywhere. So pressure is at all magnitudes, right? In this section, we obtain relations for the variation of pressure in fluids, moving like a solid body with or without acceleration in the absence of any shear stresses, motion between fluid layers relative to each other. So these are a bunch of formulas that's analyzing the densities and the changes and displacement of that point and the scalar function. And here's continued formulas here, and for rigid body motions of fluids and accelerating fluids. And so here you have Taylor series expansion of F from point A to some nearby point X. So it's not really, it doesn't really matter what it is. It's just to this point. As X gets smaller, it is common to truncate the series to first order, keeping only the first two terms on the right side. So this is just showing you how to calculate. And of course, there's also special cases. There's fluid at rest, and here's that information, and pressure remains constant in any horizontal direction. P is independent of X and Y. Special case 2, a free fall of a fluid body, and here's that formula as well, and pressure is constant. In a frame of reference moving with the fluid, it behaves like it is an environment with zero gravity. Also, the gauge pressure in a drop of liquid in free fall is zero throughout. And so just with these, with the free fall body, a free falling body accelerates under the influence of gravity when the air resistance is negligible, right? So we have to make that assumption. And the acceleration of the body equals the gravitational acceleration, which means it's a free fall, right? It's not a forced fall. And the acceleration in any horizontal direction is zero. So that means it's not falling to the side. The effect of acceleration on the pressure of a liquid during a free fall and upward acceleration. So this is just showing negative G, right, going down, and then positive G going up. Okay, and then acceleration on a straight path. And so here you can see that the free surface in the liquid. Okay, and the system in the figure behaves like a fluid at rest, except that G less A replaces G in the hydrostatic equation. And you can see that here. And you can see where this change. So we have G, and we have this angle right here that is tangent to the free surface. And so to get that, we just do G less A. Okay, and you can see that as well. You can see this tangent. Because we are taking everything normal to, right? But we don't really have a normal to. The free surface is more like that. And so therefore we have constant pressure lines. Remember, because pressure is normal to the surface. So just because we change the image doesn't mean that's going to change. And so here you have the lines of constant pressure in a linear accelerating liquid are also known as the vertical rise. And so here we do have the slope of the isobars here. And then you get your negative tan O. So this is just explaining how we get those formulas. Rotation in a cylindrical container. Okay, so here we have this axis of rotation. Up here we have work being done by that. Okay. And then consider a vertical cylindrical container partially filled with the liquid. The container is now rotated about its axis at a constant angular velocity of w. After its initial transients, the liquid will move as a rigid body together with the container. So it will eventually move with it. It will kind of catch up to it. There is no deformation, and thus there can be no shear stress, and every fluid particle in the container moves with the same angular velocity. So that's like if you were to take a straw in a cup and you were to spin it around and around and around in a circle. Or better yet, this axis of rotation, if you just put it in the center and spin it around, it will eventually speed up to a point to where it's just equal to what it is. And therefore there will be no deformation, no shear stress, and every particle in the container will have the same angular velocity. And here's more formulas to go with that, and one for free surface. We do have one for maximum height difference. Again, we're not going to get, I don't want to spend time in this video going over all of the formulas because we will just be going into them in the working videos. So here's a 6 meter spinning liquid mercury mirror of the telescope in the British Columbia. All right, and so here's the summary. We went over pressure measuring devices. We talked about fluid statics, spent not too much into that. Went over a little bit of hydrostatics in both the plane and curved surfaces, buoyancy and stability, and then as well as the fluids in a rigid body motion, which we will take into greater detail when we start working the problems.